Lesson 20. The Doppler Effect. Christian Johann Doppler, an Austrian, published a paper in 1842 where he called attention to the fact that if a luminous body, such as a star, is moving toward or away from an observer, the color, or frequency, of the star will appear different than a stationary star. For example, in this picture we have a galaxy that is stationary with respect to the Earth. We can see from the black line on the color spectrum that this galaxy has a color yellow from an observer's perspective on Earth. If the galaxy starts to move away from the Earth, the black line showing the color of the galaxy on the spectrum moves. It moves more towards orange, in the direction of red. We call this a redshift. And whenever a star or a galaxy is moving away from the Earth, it will be redshifted. It will be a little more red than its color would be if it was stationary. If the galaxy starts to move towards the Earth, the color shifts again. This time it's shifted to green. It shifted more in the direction of blue. We call this a blue shift. And anytime a galaxy or star is moving towards the Earth, it will appear blue shifted, or more blue in the spectrum than it would if it were stationary. This is the Doppler effect, and it applies to all waves, including light and sound waves. Here is an example of how the sound of a car horn changes as it moves past an observer. When a listener is in motion towards the source of a sound, the pitch frequency of the sound is higher than when the listener is at rest. In fact, if there is a relative motion between the source of the sound and the receiver of the sound, the frequency which is heard by the receiver will be different than the frequency emitted by the source. This animation shows how when the source of the sound moves, the wave fronts bunch up in front of it, becoming higher frequency, and also as it moves, the wave fronts spread out behind it, becoming lower frequency. Whenever a source of sound approaches an observer, the frequency of the sound becomes higher. Whenever the source of the sound moves away from the observer, the source of the sound sounds lower, and you have a lower frequency wave reach the observer. The equation used to calculate the frequency of the wave detected by the receiver is F equals Fs V over V plus or minus Vs, where F is the frequency detected by the observer. This is measured in hertz. Fs is the frequency of the original source, also measured in hertz. V appears in both the numerator and the denominator of the equation. V is the velocity of the sound wave. Remembering that sound will travel at a different speed in air than it would in water or in rock or in any other medium. Vs is the velocity of the source, the ambulance or the car or whatever's making the noise. In both cases, velocity is measured in meters per second. The plus or minus means that we have to decide whether to use addition or subtraction depending on the situation. We use plus when the object is moving away from the listener, and we use minus when it's moving towards the listener. For example, a fire engine is roaring past you at 15 meters per second while its 900 Hz siren is on. The speed of sound in air is 340 meters per second. What frequency do you hear the engine? A, as it comes towards you, and b as it goes away from you. This problem gives us velocity of the source equals 15 meters per second. The frequency of the source is 900 hertz, and the speed of sound in air is 340 meters per second. We're looking for the frequency detected by the observer. As it comes towards you, towards means using the minus sign in the formula. Going away from you means using the positive sign in the formula. We'll start with part A. Since frequency equals frequency of the source, v over v minus velocity of the source. We use the minus because in part A it's coming towards you. This gives us frequency equals 900 times 340 divided by 340 minus 15, giving us an observed frequency of 942 hertz. This is higher than the original 900 hertz because it's moving towards the listener. For part B, we're going to use the fact that it's going away and the positive. So the frequency equals frequency of the source, v over v plus velocity of the source. So frequency observed is 900 times 340 divided by 340 plus 15, which gives us an observed frequency of 862 hertz, which is lower than the original frequency emitted.